Welcome to the session on 3G radio network in the E2-E3 Consumer Mobility EPP upgradation course. This chapter, the main points covered are 3G standards and releases, CDMA or WCDMA concept, WCDMA codes, handovers in 3G, WCDMA channels. Coming to the evolution of mobile telephony, the first generation or 1G used the AMPS technology, Advanced Mobile Phone Service. AMPS or 1G used FDMA, Frequency Division Multiple Access, in 800 MHz frequency band. The second generation or 2G used two technologies for digital voice standards, CDMA and GSM. CDMA or Code Division Multiple Access could multiplex up to 64 calls per channel in the 800 MHz band. GSM used TDMA or Time Division Multiple Access and multiplexed up to 8 calls per channel in the 900 MHz and 1800 MHz bands. The 2G systems had some limitations. It was mainly voice oriented. It had only limited data capabilities. Worldwide roaming facilities could not be offered, and incompatible systems were used in different countries. The evolution path from GSM to UMTS. The GSM growth phases can be summarized as 2G GSM, 2.5G GPRS, 2.7G Edge, 3G or UMTS, and 4G, 5G, and so on. What is 3G? 3G is the third generation of wireless network technology that provides high speed bandwidth, high data transfer rates, good quality multimedia services. UMTS or Universal Mobile Telecommunication System is the standard for European 3G based WCDMA systems. This UMTS is managed by 3GPP or the third generation partnership project. The first commercial UMTS network was deployed in 2001 in Japan, and the development of UMTS went through a series of phases and continuous updations. The most important releases are 3GPP release 99, 3GPP release 4, which introduced the soft switching concept by introducing MGW or media gateways into the system, and the 3GPP release 5 introduced the concept of IP multimedia subsystem or IMS. Multiple access techniques. So the different systems have used FDMA or frequency division multiple access, in which the subscribers are differentiated by different frequency band allocation, TDMA or time division multiple access, in which customers are offered different time slots, and then there is the code division multiple access, in which customers are differentiated by different codes allocated to them. In CDMA, all the users can use the same frequency and transmit at the same time. They will be uniquely identified by different codes assigned to them. So the basic principle is the signal, user signal, is multiplied by a spreading signal, which is a pseudo noise code sequence, and it has a higher rate than the data rate of the message. The resulting signal will appear to be random, but if with the right code it is processed, then the intended recipient can extract back the original signal. So use of unique codes means that the same frequency is repeated in all the cells. Wideband CDMA or WCDMA is a step further in the CDMA technology, whereas the earlier CDMA versions used 1.25 MHz wide radio signals and 1.22 mega chips per second. The WCDMA uses a 5 MHz wide radio signal and a chip rate of 3.84 mega chips per second. It supports higher bit rates, has a higher spectrum efficiency, and offers higher quality of service. WCDMA concentrates on the air interface's physical layer and the procedures used in higher layers. The architecture of the air interfaces transport protocols. So we can see the radio link control layer and the medium access control layer. We look after the logical and transport channels, and in the physical layer we have bit rate processing, then chip rate processing, and the analog processing. The binary bits of the message that are processed in the bit rate processing block. Each bit is then multiplied by the unique code assigned to the subscriber, and it is further enhanced into chips. The data rate will be higher. Now we have chips and chip rate processing. Then further processing is done to transfer the messages, the chips, onto the physical channels for carrying over the medium of communication. When the data enters the physical layer, the data rate is typically 12.2 kbps. After the addition of error detection and correction codes and some rate matching processes, the bit rate becomes 30 kbps, and each bit is then converted into 128 chips to produce a chip rate of 3.84 million chips per second. This is the diagram that depicts the downlink channelization and dechannelization from a base station to a single mobile user. Okay. We can see two bits are being transmitted. Bit 1 is 1 and bit 2 is -1. We are using a 8 chip code for uniquely identifying this customer, and the code is 1111 -1 -1 -1. So these 8 chips form the user's code. So the bit is multiplied by this code, and the resulting chips are being transmitted over the medium. Bit 2 is -1. Again, this is multiplied by the unique code, and the resulting chips are transmitted to the user. At the user end, the chips received are again multiplied by the original code of the user, which is the dechannelization code, and the resulting bits are summed up to get a soft decision. So the chips are multiplied by the code, and the resulting chips are summed up to get the soft decision. So the soft decision, the sign of the soft decision tells you what is the bit that is transmitted, and the magnitude tells you what is the confidence level of that estimation. So +8 means bit transmitted was +1, and 8 denotes that it offers a high confidence level. So if it is +1 or +2, that means the confidence, the probability of the decision being correct is less. So soft decision 8 and -8 are made, and then based on the sign of the decision, the hard decision is made about the transmitted bit, which is 1 and -1. So the user is able to retrieve the transmitted bits. So the base station assigns the mobile a code, it is called a channelization code or spreading code, and the chip rate is normally fixed in the case of UMTS FTD to 3.84 MCPS. The number of chips per bit is called the spreading factor. In the example that we have seen before, the spreading factor is 8. Your code consisted of 8 chips. And the bit rate equals the chip rate divided by the spreading factor, and error correction has also been already applied to these bits. So the original data rate is much lower than this rate. And then the important point to note is that the channelization codes, the unique codes given to each subscriber, are orthogonal. That is, if we multiply the code given to each subscriber, we multiply the codes chip by chip and sum up, then the result will be 0. So now let's look at the example of the downlink channelization and dechannelization from a single base station to 2 mobile users. Okay, so there is user 1 and user 2. A bit, one bit is sent to each user. The first user is being sent bit 1 and the second user -1. So both the users have been given 2 orthogonal channel codes. The bit is multiplied by the corresponding channel code, and the resultant value, the chips, are being sent towards the users on the air interface. Okay. So the bit multiplied by the code, getting a resultant value. The sum of all the users' signals are being sent on the medium. So user 1 and 2, they both receive this information. Each will dechannelize or try to extract the original information by using their own respective codes. So user 1 multiplies the received signal with his code, and he is getting a resultant value. Again, the values are summed up. User 2 also multiplies the received information with his own code and gets a resultant value. We can see the soft decision made by user 1 tells him with a confidence level of 8 that the bit intended for him is +1, and similarly user 2 is able to make a decision that the bit sent for him is -1. Now the total overall processing procedure involved in a WCDMA system is shown here. We have a source coder, then followed by channel coding, then spreading, modulation, and transmission over the radio channel. At the receiver end, there is a reception and the reverse of all the processes that have taken place in the transmission link: demodulation, despreading, channel decoding, source decoding, and finally the signal is retrieved back. So the source coding increases the transmission efficiency of your input signal. In channel coding, error detection and correction capabilities are introduced. By using multi-level spreading, we increase the capability of the signal to overcome interference. And through the modulation technique, the signals are converted into radio signals for transmission through the channel. At the receiver, the reverse of all these processes are carried out to recover the information signal back. Next, we are going to look into WCDMA codes. 2 categories of codes are used with the UMTS WCDMA systems: the channelization codes and the scrambling codes. Channelization codes are orthogonal codes based on OVSF technique, orthogonal variable spreading factor technique. The codes are fully orthogonal. They do not interfere with each other and are time synchronized. The codes can separate transmissions from a single source. And in the downlink, they can separate different users within a single cell or sector. The OVSF codes are picked from the code tree. We'll see what the code tree is. We can think of the code tree as a family tree in which each channelization code has two children, one made by repeating it and the other by repetition and inversion. Okay. Now we have a code 1 1. So it will have two children. The first one is formed by repeating the code and the second by repeating the code after inversion. So 1 1 minus 1 minus 1. Now this code 1 1 minus 1 minus 1 has again two offsprings. The first formed by repeating the code 2 times. The second is formed by repeating the code once and then repeating with inversion. 1 1 minus 1 minus 1 becomes minus 1 minus 1 1 1. So this is how we form the code tree. Now the number of orthogonal codes available is equal to the spreading factor. It is spreading factor 8. If it consists of 8 chips, that means there are 8 orthogonal codes. And the spreading factors are always a power of 2. The release 99 used a spreading factor from 4 to 512 and 4 to 256 on the downlink and uplink respectively. The code tree, as we have seen in the illustration, can only accommodate a limited number of mobiles. So there is a need to reuse the codes in every cell. But this may result in crosstalk between two transmissions if two nearby cells are using the same frequency and the same code. So this issue is solved by introducing a second set of codes known as scrambling codes, and each nearby cell is assigned a different scrambling code. Now the scrambling codes are again made up of chips, but they have a much longer repetition period than the channelization codes. So about 10 millisecond duration, that is 38,400 chips. So in UMTS there are enough scrambling codes to label 512 different cells. So this is a quite large number, and the cells that will be using the same scrambling code will be a large distance apart, and so the problem of crosstalk is eliminated. The scrambling codes should also be ideally orthogonal to each other, but in practice we are using a pseudo random number generator to make the scrambling codes, and they will be uncorrelated. So if we multiply two scrambling codes together and add up the results, then the total is 0 on the average, but not necessarily identically 0. So they are only uncorrelated, not compulsorily orthogonal. Now the effect of using uncorrelated codes is illustrated in the example that we are going to see now. So from 4 cells with different scrambling codes, transmissions to a different mobile are studied. The spread factor is 4. So for each bit we will multiply that by a code which has 4 chips, and each mobile will receive a signal from the corresponding node plus interference from the other 3 nodes. So for making the illustration simple, we are assuming that the channelization codes 1111 has been used throughout in all the cells. And because the scrambling codes are only uncorrelated and not orthogonal, the mobiles will receive some interference from the neighboring cells. So we have 4 node Bs, 1, 2, 3, 4, and they are sending to 4 users, user 1, 2, 3, 4. Now the scrambling codes used in the 4 cells are shown here. So different bits are being sent to the users. each bit is multiplied by the unique code, and the resultant chips are transmitted. So each user will get the total sum of all these values. So this will be the received chip. As in the previous examples, each user will multiply with the descrambling code, corresponding descrambling code, and the resultant value, all the values are summed up to get the soft decision. And here we can see the soft decision tells that it is a plus 1 bit, minus 1 bit, plus 1, minus 1, but the confidence of the estimate, the magnitude of the soft decision is only 2, whereas in the previous cases we have seen magnitudes of 8. So based on the sign of the soft decision, the hard decision is made that bit 1 has been transmitted, bit minus 1, bit 1, and bit minus 1. So as we can see, because of interference from neighboring cells, sometimes the bits are detected wrongly. So this will be taken care by the error detection, error correction capabilities of the channel coding. Now we come into the network architecture of UMTS. So in the network architecture, mainly we have 3 parts: the user equipment, the access network, and the core network. So the access network is also called the UTRAN, UMTS terrestrial RAN, where RAN stands for radio access networks. So in the network architecture, we will be studying the different elements that constitute these parts and the interfaces. The interfaces are the logical connections between the network elements. So here we can see in the lower half we have the different user equipments. They are connected by wireless radio channels to the UTRAN part. As we can see, it consists of 2 major modules, node B and RNC. And then UTRAN is connected to the core network. The core network, we can see 2 parts: CS, that is the circuit switched network, and PS, that is the packet switched network. And between all these elements we have interfaces, logical connections. The user part to UTRAN, we have the UU interface. From node B to RNC, we have the IUB interface. Between RNCs, we have IUR interface. And from RNC to the CS and PS part of core network, we have IUCS and IUPS respectively. So in WCDMA, the RAN or the radio access network provides connection between the user equipment, between the handset and the core network, and it isolates all the radio issues from the core network. And one major advantage is that one core network can support multiple access technologies. Coming into the node B, radio base station. The radio base station handles the radio transmission and reception from the user handset over the radio interface, which is UU. It is controlled from the RNC or radio network controller through the IUB interface. One radio base station can handle one or more cells. Functions of node B: radio transmission and reception handling, involved in mobility management, involved in power control, modulation and demodulation, closed loop power control. The radio network controller or RNC controls all WCDMA RAN functions. It connects the RAN network to the core network through the IU interface. RNC has two distinct roles to play: to serve and to control. The serving RNC has overall control of the handset that is connected to the WCDMA RAN. It controls the connection on the IU interface for the handset and terminates several protocols in contact between the handset and the WCDMA RAN. The controlling RNC has overall control of a particular set of cells and their associated base stations. The RNC connects to node B through IUB interface and to other RNCs through IUR interface. The RNC and node B together form the radio network subsystem. Main functions of the RNC include radio resource management, call management for the users, connection to the circuit switched and packet switched core network entities, and radio mobility management. When a handset needs resources for a call not controlled by its serving RNC, the serving RNC asks the controlling RNC for these resources. The request between the RNCs is made via the IUR interface, which connects the two RNCs. In this case, the controlling RNC is also termed as drift RNC for this particular handset. The main service offered by WCDMA RAN is the Radio Access Bearer or RAB. To establish a call connection between the handset and the base station, a radio access bearer is needed. The characteristic of the RAB depends on the kind of service or the type of information that is to be transported. So RAB carries subscriber data between the handset and the core network. So it is composed of one or more radio access bearers between the handset and the serving RNC and one IU bearer between the serving RNC and the core network. So 3GPP has identified 4 different classes of RAB. First one, conversational, which has low delay and strict ordering characteristics. Example, voice telephony. Second, streaming RAB, which offers moderate delay and strict ordering. Example, watching a video clip. Interactive RAB, which offers moderate delay characteristics. Example, used for web surfing. And the last one, background RAB, in which there is no delay requirements. Example, for the case of file transfer. For optimal operation of a complete wireless system, that is from handset to the radio access network, several functions are needed to control the radio network and the many handsets using it. Okay. We can see a GSM bar WCDMA architecture where both the GSM and the WCDMA share a single core network. Now, a major functionality involved is the power control. Power control regulates the transmit power of the terminal and the base station so that there is less interference and more users can be allowed on the same carrier. So the base station, it should receive the same power level from all handsets irrespective of their distance from the base station. Now WCDMA has a fast power control that updates the power levels at 1500 times every second. So in order to ensure a good performance, power control is required both in the uplink and downlink directions. Power control also gives rise to a phenomenon called cell breathing, which is a trade-off between coverage and capacity. That is, the size of the cell will vary depending on the traffic load. Now, handover is another functionality required. Handover enables the handset to maintain the continuity and quality of the connection while moving from one cell to another. Two classes of handovers are discussed: soft handover and softer handover. With soft handover, the handset can communicate simultaneously with two or more cells in two or more base stations. The handset adjusts its power to the base station that requires the smallest amount of transmit power. In soft handover, the handset is connected to multiple cells at different base stations. In softer handover, the handset is connected to multiple cells within the same base station. So a drawback with soft handover is that it requires additional hardware resources on the network side, as the handset has multiple connections. So in a well-designed radio network, about 30 to 40% of the users will be in the handover mode. The illustration explains the soft and softer handover. Softer handover within a single base station, and soft handover between different base stations. So there is also the inter-system handover, where handover from WCDMA system to GSM system occurs. So when WCDMA was standardized, a key aspect was to ensure that the existing investments could be reused to the maximum extent possible. The handover between the new network and GSM, which can be triggered by the needs of coverage, capacity or service requirements. The function related to inter-system handover is the compressed mode. So when performing handover to GSM, measurements have to be made in order to identify the GSM cell to which the handover will have to be made. So in the compressed mode, the information will be transmitted during the first 5 milliseconds of the frame. That is, the information is compressed to the first half of the frame, and the remaining half, 5 milliseconds, will be used for these measurements, the measurement regarding the handovers. Then there's the intra-system handover or the inter-frequency handover. So it occurs in high capacity areas where multiple 5 MHz WCDMA carriers are deployed. Inter-frequency handover is the handover between WCDMA carriers on different frequencies and has many similarities with the GSM handover, like the compressed mode functionality. So as a conclusion to this chapter, WCDMA is a very successful technology due to its robust radio network design, and 3G has got add-on features with the introduction of high-speed packet access, HSPA and HSPA+. So that's all in this chapter. Thank you.